Good. So yeah, y'all can go ahead because it's time.
Okay, good morning, everyone. We are group 4 and we'll be presenting on the hyperbola. And our objectives for today is that we're going to look at the definition of a hyperbola. We are going to identify key components of a hyperbola. We are going to interpret the standard equations of a hyperbola, solve problems involving hyperbola, and graphing hyperbolas. So the definition of a hyperbola reads that a hyperbola is the set of all points in the plane, the difference of whose distances from two fixed points is a given positive constant. Now in this definition, the difference of the distances means the distance to the farther point minus the distance to the closer point. Now the fixed point we are talking about here is the focus, and we have two of them. So the fixed points refer to the foci, which is the plural of focus. We're going to see more about that as we go on. So here we're seeing that the two fixed points are called the foci, which is the plural for focus. So we have one here and we have one here. The midpoint of the line segment joining the foci is called the center of the hyperbola. So if we look on this axis here, we're going to see that the foci is on this line here, which is the x-axis actually. And the midpoint is the center. So from this foci to the center, and this focus to the center, and this focus to the center, therefore, these distances must be equal because the center is this point is the center of the hyperbola. The line through the foci is called a focal axis or the transverse axis. So the transverse axis is this horizontal line, which is actually the x-axis. So we can refer to it as the focal axis or the transverse axis and also the major axis. The line through the center and perpendicular to the transverse axis is called the conjugate axis. So this is the line through the center that is perpendicular to the transverse axis, which is the same as the y-axis. So this axis is called a conjugate axis. The hyperbola intersects the transverse axis at 2 points called vertices. So we have two vertices. We have one here, this point here, where this hyperbola intersect the x-axis or the transverse axis, and we have another one here. The two separate parts of a hyperbola are called the branches. So we have one here and we have the other one here. These are called branches. So let's look at the standard equation of a hyperbola. So we're gonna look at a few things first. Now here we're saying that the distance between the vertices is denoted by 2a. Now if we look at this diagram here, we are going to see that we have one vertex here and we have the other one here. And the distance from here to here, or from one vertex to the other, is 2a. That means that the distance from one vertex to the center is a, and the distance from the other vertex here to the center is a. That's how we get 2a. And we see that the distance between the foci is denoted by 2c. So we have one focus here and we have another one here. So the distance from this focus to the center is c, and the distance from this focus to the center is c. That's how we get 2c. And we say that the quantity b is defined by the root of c squared minus a squared. So b is the distance from the center to the conjugate axis endpoint. And we're going to see more about that as we move along. Now, if V is one vertex of a hyperbola, then the distance from V to the farther focus, so let's look at this vertex here, the distance from V to the farther focus, so that's from here to here, V to the farther focus, minus the distance from V to the closer focus, which is this distance here, V to the closer focus. And that distance is a positive constant, which is 2a. So that is what this is telling us here. C minus a plus 2a minus c minus a is equal to 2a. So we are going to let P, which is xy, be any point on the hyperbola so that the distance from P to the farther focus, so P is this point here, xy, the coordinates are xy. So we are going to take the distance from P to the farther focus. So that's from here to here, minus the distance from P to the closer focus, which is here to here, is 2a. So this is how we get our positive constant 2a when we minus this distance from this one. So we can represent that using the distance formula. So we can say that the root of x plus c all square plus y square minus the root of x minus c all square plus y square is equal to 2a. Now, we're taking the absolute value here of the difference because we need a positive constant, not just any constant. Now we're going to square both sides of this equation. When we square both sides, we're going to end up with this x plus c all square plus y square minus 2 times the root of x plus c all square plus y square times x minus c all square plus y square plus x minus c all square plus y square is equal to 4a square. Now, when we simplify this and we isolate the radical, and then we square again to remove the radical, it will give us x squared over a squared minus y squared over b squared equals 1. Now, this is the standard hyperbola equation, for when the origin is the center. And here we can see we have a relationship between A, B, and C. So this relationship is expressed using the Pythagoras theorem, where c squared is equal to a squared plus b squared. Now we're going to look at the orientation of the hyperbola when the origin is the center. So the orientation of a hyperbola is determined by noticing where the minus sign occurs in the equation. So let's look at the first one here. So we're seeing here that the foci is on the x-axis or on the transverse axis. Therefore, the conjugate axis is the y-axis. And the center is at the origin where it's 0, 0. So when our foci is on our x-axis or on our transverse axis, then our hyperbola will look like this. And our equation will be x squared over a squared minus y squared over b squared is equal to 1. And we can say that this hyperbola is horizontally oriented. So what we can look at is the minus sign. Or we can also say that when our x squared term is positive, then the orientation will be horizontal. Our hyperbola will look like this. The second diagram, we see that the foci is on the y-axis. So the conjugate axis is on the x-axis and the center is the origin. So this time, our transverse axis is actually on the y-axis and our conjugate axis is on the x-axis. And our equation will look like this: y squared divided by a squared minus x squared over b squared is equal to 1. So in this case, you can see the difference here. The minus sign was in front of the y squared. Now it's in front of the x squared. So when our y squared term is positive, we will have a vertically oriented hyperbola. Now we must note that the vertices has coordinates plus or minus a, 0, or 0 plus or minus a. Now for this hyperbola here, y is plus or minus a. So a is our vertex. Now we have two branches, one on the positive region and one on the negative region. So that is why here we will have a positive a value and here we will have a negative a value. When we look at the second one here, we're gonna see that our vertex is on the y-axis, or our conjugate or our transverse axis is the y-axis this time. So that's why we'll end up having our a value this part where the y value is. So it's positive here and it's negative here. And also the foci has coordinates plus or minus c, 0, or 0 plus or minus c. So when the hyperbola is horizontally oriented, then our c value, which is the foci, can be plus or minus, because this one here is on the positive region, so it will be plus c, and this one here is on the minus region or area, so we have negative c. And same here, plus c, minus c. So we're saying here that another way to determine the orientation of the hyperbola is to equate one of the terms to 0. So here we have an example. So this is another way to determine whether we'll have a vertically or a horizontally oriented hyperbola. So does the hyperbola x squared over 4 minus y squared over 9 has its focal axis on the x-axis or the y-axis? So this time we're going to let x equal 0 in the equation. So if x is equal to 0, then this whole term here disappears, right? So we're left with minus y squared over 9 is equal to 1. And here we'll see that y squared will be negative 9. We cannot square root this negative number, so this equation has no real solution. So the hyperbola does not intersect the y-axis. Now, if we let y equal to 0 in the equation, then this part goes out and we have x squared minus 4 is equal to 1, and x is equal to plus or minus 2 because we take the square root of 4, so we'll have plus or minus 2. Now, this tells us that the vertices are at the points negative 2, 0, and 2, 0. So we conclude that the focal axis is on the x-axis. And here the diagram is showing. So our vertices are at the point negative 2 and positive 2. And the orientation is horizontal. So here I have an equation. So we are going to try to determine the orientation of these equations of hyperbola. So the first one is x minus 3 squared, sorry, it is supposed to be a square, divided by 4 minus y plus 2 squared divided by 9 is equal to 1. So we want to determine whether this equation is going to give us a vertically or a horizontally oriented hyperbola. So we have to first look at the minus sign. Right now it's in front of the y squared term, which means that our x squared term is positive. So then our result will be, we have a horizontally oriented hyperbola here. Will look something like this. And in the second case, we have y minus 5 squared divided by 36 minus x plus 3 squared divided by 49 is equal to 1. Now, in this case, our y squared term is positive, or the minus sign is in front of the x squared term. Therefore, this will result in a vertically oriented hyperbola. So it will look like that. I now hand you over to my other colleague who will continue with the presentation.
Good morning. Hi, miss. There's nothing showing on the screen. Alright, so the eccentricity of a hyperbola basically measures how stretched the hyperbola will be. Now, the eccentricity of a hyperbola is always greater than 1. And we have our formula here, which is E, which will be represented by or denoted by eccentricity, which equal to C over A. Now, as E becomes larger, the branch of the hyperbola becomes more flattened, stretching farther along the transverse axis, which is known as also the x-axis. But if E is closer to 1, then the hyperbola is more compact, which means it will be closer to the vortex or vortices. Now, each pair of horizontal or vertical standard form hyperbola, the properties remain the same regarding eccentricity, which means we'll always be using the formula E is equal to C over A. Now, let's look at the example given on the right-hand side. So it says x minus 2 all square divided by 9, subtract y plus 3 all square over 16 is equal to 1. Now, to find the eccentricity of the hyperbola, we're going to use the same formula, but where C will be equal to, as Miss said in her explanation, the root of A square plus B square. Now, when she was explaining the formula, it was x squared, x over y squared minus y over b squared. Now, in this example, a square is going to be equal to 9 and b square is going to be equal to 16. Now, when we substitute this into the formula, it's going to be 9 plus 16, which will give us 25. We will square root that 25, which will give us 5. Now, the eccentricity of that hyperbola will be C, which is 5 over A. Now, how we have 3 here, remember A squared was equal to 9. Now, we did not want A squared, we wanted A. So to find we will square root the 9, and the square root of 9 will give us 3. That is how we have the eccentricity being 5 over 3. Next page. Now, the acetones of hyperbola are lines that the hyperbola approaches but never reach. Now, there are 2 instances for the acetones. Now, when the minus sign is in front of the y square value, then the acetones will be y equal to b over ax and y equal to minus b over ax. Remember, Miss was explaining in her explanation at first that to determine whether the hyperbola will be horizontal or vertical, we look at where our minus sign will lie. Now, on the right-hand side, there are 2 diagrams. When the acetone the y square is minus, you will be looking at the diagram on the left-hand side. So the 2 red lines are what we call acetones. If you can see in the diagram here that Miss is showing, the 2 dotted red lines, or broken red lines, should I say, are the acetones. Now, the next instance that I was referring to is when the x square has the minus sign in front of it. The acetones is going to be y equal to b over y equal to a over bx, and y is going to be equal to minus a over bx. So when the minus sign is in front of the y, we'll have our b values as our numerator and our a values as our denominator. And when our x value is in front of, when the minus sign is in front of our x value, or x squared, is going to be our a will be our numerator and our b will be our denominator. Let's be searching the next slide. Now, when we're dealing with acetones, there is a trick that we can use to avoid memorizing the formula, and that is substituting 0 for 1 on the right-hand side of the hyperbola equation. And then we'll solve for y in terms of x. Now, on the right-hand side, we have x squared over a squared minus y squared over b squared, which is equal to 1. So there are 3 ways that this can be written. The first one is a squared over b squared minus y squared over b squared equal to 0, or y squared equal to b squared over a squared x squared. Or we can have y is equal to plus or minus b over ax. Now let us look at the example in front of us. Now, to find the 4 sides, we're going to find the 4 sides, the vortices and acetones of the hyperbola, given the equation y squared over 16 minus x squared over 9 equal to 1. And we also have to sketch the hyperbola. Yes. So since the minus sign is in front of the x squared term, the hyperbola will have its 4 sides on the y-axis. Now, the standard form, what Miss was explaining, was y squared over a squared minus x squared over b squared equal to 1. Now, because the minus sign is in front of the x squared, we don't know that our hyperbola will open up vertically. So given the standard formula, a squared will be equal to 16 and b squared will be equal to 9. Now, we don't want to find what b squared, if we want to find what is a alone and b alone, we will square root 16 giving us 4, square root 9 giving us 3. Since a is 4, then our vortices are 0 on the x-axis, 0, and on the y-axis we'll have -4. And then on the x-axis we'll have 0, and on the y we'll have 4. Now, using our eccentricity formula, we will have a square plus b, the root of a square plus b square, which will be 16 plus 9 would give us 25. The square root of 25 will give us 9. So the 4 sides are 0, -5, and 0, 5. Now, to obtain the acetones, we will substitute 0 for 1 in the given equation. So we'll equate our equation to 0, which will be y equal to plus or minus 4 over 3x. And here on the right-hand side, we have our sketch. We'll have our sketch hyperbola. Remember I said because the minus sign is in front of the x term, our hyperbola will open up vertically. And our vertices are 0, -4, and 0, 4. As you can see, Miss put the 2 dots there. And then we have our acetones being 4 over 3x and -4 over 3x. Mama. Next slide, please, Miss. Mama. Just now. Mama. So here we have a next example. So let's consider the vertices of the hyperbola at positive or -6, 0. The acetones described by the equation is y equal to positive or -5 over 6x. Find the equation of the hyperbola. Just now. So the vertices of the hyperbola will be positive or -6, 0. This means that a hyperbola center is at the origin 0, 0. And the distance from the center to each vertex along the x-axis is a equal to 6. Now, the acetones will determine the equation of the hyperbola. Now, the form of the hyperbola will be x squared over a squared minus y squared over b squared equal to 1. Now, the acetones given is y equal to positive or -5 over 6 x. So, therefore, it's b over ax. So when we substitute b over ax, it's going to give us 5, we're substituting a, right? So it's going to be 5 over 6. Now we're going to solve for b. B is equal to 5. So the equation of the hyperbola, substituting a 6 and b is equal to 5 into the standard hyperbola formula, the same formula that I mentioned before, x squared over a squared equals, minus y squared over b squared equal to 1. So when we substitute, this is going to give us x squared over 6 squared minus y squared over 5 squared equal to 1, giving us x squared over 36, because 6 will give us 36 and 5 will give us 25. So it's going to be y squared over 25 equal to 1. And I'll hand you over to the next presenter.
Good morning, everyone. I'll be presenting an equation of a hyperbola when the center is not at the origin. If the center of the hyperbola is at the point HK and its focal and conjugate axes are parallel to the coordinate axis, then the equation has one of the forms. So when the axis is parallel to the x-axis, you're going to use this equation. And when the axis is parallel to the y-axis, you're going to use this equation. Note that the vertices has coordinates h plus or minus a to k, and the 4c has coordinates h plus or minus c to k. The deviations are similar to those of the parabola and eclipse. The equation of asymptotes can be obtained as before by replacing 1 with 0 on the right-hand side and then solving x in the y in the x term. Have an example here. show that the curve x square minus y square minus 4x plus 8y minus 21 is equal to 0 is a hyperbola. Sketch the hyperbola and shows the forces, vortices, and the asymptotes. So when solving this, first we have to group the x term and the y term, and then taking the constant to the right. After finishing this, we're going to square it, completing the square, which gives us x minus 2 all square minus y, 4 minus y square equal to 9. Next, we're going to divide throughout by 9 to introduce the 1 on the right-hand side. If you're wondering how we have the center 2 to 4, in the formula, we see that h is where the 2 is in the x minus 2 square, that's the h, and the k is the 4 where y minus 4 is. So that our center point is hk, which is 2 to 4. So our vertex A is equal to 3. How we have 3? In the formula, a square is where 9 is. So when 3 square is equal to 9, so that's why a is equal to 3. So the vortices are located at 3 units to the left and 3 units to the right of the center of the points. -1 to 4 and 5 to 4. How we have -1 and 4 and 5 to 4? The coordinates vortices in the far side, if you saw, h plus or minus a to k. So when we plug in that, we end up with -1 to 4 and 5 to 4. B is equal to 3. 9, we square 3 and we end up with 9, so that's why B is 3. The forces formula is C square root A square plus B square. Plugging in that, we end up with 3 square root 2. So the forces are located at 3 square root units to the right and the left of the center, or at the point 2 negative 2 subtract 3 square root 2 to 4 and 2 plus 3 square root 2 to 4. Here we have the diagram of the sketch. As you can see, the forces points are here and here. Next slide, miss. So now we have to find the asymptotes. So by substituting 0 for 1 equation, we have y minus 4 equal to plus or minus x minus 2. Now work out that, we end up with x plus y is equal to x plus 2 and y is equal to negative x plus 6. So this diagram represents the
hyperbola, it is called an equilateral since A is equal to B. For such hyperbolas, the asymptotes are perpendicular, as you can see on the diagram. I'll now hand you over to the next person.
Good morning, everyone. I'll be looking at the latus rectum of the hyperbola. What is that? The latus rectum of a hyperbola is defined as a line segment perpendicular to the transverse axis and passes a focus of the hyperbola with endpoints on a hyperbola itself. As you can see in this diagram here, as one of my colleagues mentioned earlier, the transverse axis is the horizontal axis, as you can see that there. And the two diagrams there, the hyperbola, which is the two curves, you can see the point at the center, that's the center at A. And my colleague also mentioned that we have two A's here and two C's. Next purpose. We are going to look at the length formula on how to calculate the latus rectum. We'll be using this formula here, 2b squared over A. Endpoints on how to calculate the latus rectum. We have positive or negative C. What is C? C is the focus, plus or minus b squared over A. And this formula here will be used for the hyperbola when it is at the center. Now for a hyperbola, when it is not at the center, at the origin, we will use this formula. H plus C, comma, K plus or minus B squared over A. And H minus C, comma, K plus or minus B squared over A. What is H and K? These are the coordinates of the center. And we know that C is the focus. In this case, we have two focus, which is a plural for foci. Next slide, miss. Now we're going to look at some example. Here I have a question. Consider a hyperbola with the equation x minus 2 all square over 9. Subtract y plus 3 all square over 16 equal to 1. We know that this is a general formula that my colleagues mentioned earlier. So we are going to do two things. Number one, we are going to calculate the length of the latus rectum. And number two, we're going to determine the coordinates of the endpoints of the latus rectum. How do we do that? Calculate the length of the latus rectum of a hyperbola is given by this formula, 2b squared over A. All we need to do is to substitute the values of A and B. In this case, we know that A is 9 and B is 16. Now, the formula that to find the length here, we know that we just substitute 2 multiplied by 16 all over 3. This will give us 32 over 3. How do we find the endpoints of the latus rectum? Here we just substitute the values in the formula given that I mentioned earlier. H plus or minus C, K. We know that H is equal to 2 and K is equal to negative 3. How do we find the focus or the two foci? We use the formula here. C squared equal A squared plus B squared. And we will find the foci. So we get that. That will be equal to the square root of 9 plus 16, which is give us the square root of 25. And as you can see, the value for the square root of 25 is equal to 5. As you can see there, that's how we derive at C, the value for C, which is equal to 5. Therefore, the endpoints of the latus rectum for each focus are, we have 7, comma, minus 3, and we have 7 minus 3 plus or minus 16 over 3. For the other focus, we have negative 3, comma 3. In this case, we have the endpoints. So I would like to do a little annotation here. So as you can see, for the foci, for the first one, we have the point 7 minus 3. So as I go on the graph, it should be somewhere there. And for the other one, it is -3, -3, which should be somewhere around there. So as I draw these lines here, you can see that this point here will have the endpoints. We have one endpoint here, which is A. You can call the other one B. Next one C, and the other one D. When we work out these values for A, we'll have 7, 2 and 1/3, and for the B, we will have 7, -8 and 1/3, and for C, we'll have -3, 2 and 1/3, and for D, we'll have -3, -8 and 1/3. Thank you. I will now hand you over to the next presenter, who will tell you more on the hyperbola.
Sir, can you please erase?
All right, good morning, everyone. So I'll be presenting on hyperbola and intersecting lines. So a line intersecting a hyperbola is a straight line that crosses the hyperbola at one or more points. Depending on its position relative to the hyperbola, a line can intersect the hyperbola at 2 points, 1 point, or none at all. All right? So when we think about that last line, a line can intersect it at 2 points, 1 point, or no point at all. We can think of quadratics, right? Because we have there the maximum of 2 points. So in that case, we know that we're going to be dealing with a quadratic equation. So to find the intersection, the points of intersection with the hyperbola, we substitute the equation of the line into the equation of hyperbola and solve for the points of intersection. So to determine whether the line intersects the hyperbola or not, we have to calculate the discriminant. So see, again here, we're dealing with a term that is used normally with quadratics. So if we look at the right, at the topmost graph, we will see that the line there is cutting the hyperbola at 2 points, right? So the diagram under that one now has it only at 1 point, and the one at the bottom there has it at no points at all. So we're going to now figure out how exactly we're going to know whether the line cuts once, twice, or not at all by using the discriminant. So firstly, if the discriminant is less than 0, the quadratic equation has 2 real points. So the line intersects the hyperbola at 2 points, right? As we can see on that diagram. But if the discriminant is equal to 0, the quadratic equation only has 1 real repeated solution. So the line will intersect the hyperbola at exactly 1 point, or the line is tangent to the hyperbola. And lastly, if the discriminant is less than 0, then it has no real solution. So therefore, the line and the hyperbola do not intersect. So if you'll notice, they go in order with the diagrams. The points, they go in order with the diagram. Yes. Next slide, please, miss. So now we're going to do an example. So we have the equation of a hyperbola being x squared over 4 minus y squared over 9 equals to 1. And the equation of a straight line being y is equal to 2x minus 1. So we want to find the points of intersection. So the first thing we do is we substitute the straight line equation into the hyperbola. The reason being is that if these points, if the hyperbola and the straight line intersect, therefore that means that they have the same x and y coordinates at that point or at multiple points, because it can cut the hyperbola at 2 points. So first we substitute, and then we see there that we have a y square, not just y. So we square the equation of the straight line. So that's 2x minus 1. We square that and we end up with 4x squared minus 4x plus 1. So after we put that into the equation of the hyperbola, we know then we combine it into a single fraction by finding the LCM. So it becomes 9x squared minus 16x plus minus 12x plus 3 over 36, which is our LCM, equals to 1. After that, we simplify now, and we minus the 16x squared from 9x squared. That gives us negative 7x squared. So we eliminate the denominator now by multiplying both sides by 36. So we end up with negative 7x squared plus 12x minus 3 equals to 36. So we've now written our equations after we've substituted one into the other. We've now put it into a quadratic form. So now we equate the whole thing to 0, and we solve the quadratic equation using the quadratic formula. So after we substitute b and a and c into the equation, we ended up with 12 plus or minus the square root of 144 minus 1092 over 14. Now, as soon as we look at that part there, 144 minus 1092, we can immediately tell that, okay, that's going to give us a negative answer. So we know now that we're not going to get any real x values there, because if we do that, we're going to end up with negative 948. So we have to find the square root of that, and that can't work out, not with the quadratic formula. So by that result, we can see now that there's no real results, and there are therefore no real solutions. So the line and the hyperbola do not intersect at all. Right? That concludes my part of the presentation. I'll now hand you over to Ms. Mala.
Good morning, everyone. I'm tasked with explaining the equation of a tangent line to a hyperbola. Now, a tangent to a hyperbola is a line that touches the hyperbola at a single point, and it's called the point of contact. We have here a diagram to explain or to show this. So at this point here, that is one point of contact, or the tangent, and then we have another one there as well on the other hyperbola. The next, please. Now, a hyperbola is centered at the origin or midways horizontal. We have the equation, the general equation, x squared over a squared minus y squared over b squared equal 1. A tangent at the point x1, y1 on a hyperbola, this satisfies the equation. Miss the equation, please. The equation, we insert the x point, so we have x times x1 over a squared minus y times y1 over b squared equal 1. Just stick it into that formula. We'll be using it soon. If we have a hyperbola centered at the origin in this vertical, we use our general equation as well again. And a hyperbola that is not centered at the origin, we would use x squared minus h x minus h all squared over a squared minus y minus k all squared over b squared equal 1. Again, we have the other equation for point at a tangent, and if we have to write the slope form of a tangent line, then we would use y equal mx plus or minus the root of a squared times m squared minus b squared. So those are some general formulas that we'll be using. Next slide, Miss. So I have an example here. It says find the equation of the tangent to the hyperbola x squared over 9 minus y squared over 16 equal 1 at the point P, which is 2, 3, 2 on the hyperbola. Now remember, when we're given a point, like what we have here, we're given the point P, that is the point of contact or point of tangency. We would use the equation x times x1 divided by a squared minus y times y1 divided by b squared equal 1. We know that a squared is 9, so a would be 3 and b squared is 16. And if we want to know b, we will find the root of 16, which will be 4. And we have our point P, which is 3, 2, and that lies on the hyperbola. Now all we gotta do is substitute these values into the equation that we have, general equation. So we have x times x1, which is 3 over 9, and we minus y times y1, which would be 2 over 16 equal 1. When we simplify this, we can just reduce, so we'll have x over 3 minus y over 8 equal 1. What we can do is we can solve this, go ahead and find the LCM. So we work it out. We'd have x squared minus 3y equal 24. Then we want to write this here in terms of y equal mx plus c. So we write it in terms of y. So we have y is equal to 8 over 3x minus 8. So then we know our y-intercept would be, for this tangent would be -8. And I have a diagram here or sketch to show this. So we have the point of contact, which is at 2, 3, 2, sorry. And then we have our y-intercept at -8. And that is our tangent to the hyperbola. Next slide. Now the reflection property of hyperbolas, a line tangent to a hyperbola at a point P makes equal angle with the line through P and the foci. Now I have a diagram showing that here we have our focus 1 and then our focus 2. We have a tangent and it touches the hyperbola at point P. So the angle between focus 1 and P and the angle between P and focus 2, which we have alpha and beta, these two angles are equal. Next one, please. The reflective property of a hyperbola states that if a ray of light passes through one focus of the hyperbola, it will be reflected along the line from the opposite focus. Now we have on this diagram, the next diagram at the bottom, we have a light ray originating from focus 1 and it's hitting the point P on the parabola. The reflective ray would travel directly from the other focus because of the symmetrical way the hyperbola splits the distance. And this happens due to the law of reflection, which states that the angle of incidence equal to the angle of reflection. So as you can see in the diagram, we have the angle of incidence and we have the angle of reflection. These two angles are equal. Now that brings us to the end of our presentation. Next slide. Is there any questions or comments? Thank you.
So no questions with that? That means you all are ready for that test. Did I hear any mention of the eccentricity of the hyperbola?
Yes, sir.
You did talk about that? Trying to remember, I'm not seeing anything. Little bit. Oh, maybe I missed that. All right, yeah. All right, not bad. Very good. Yeah. So I'll stop the recording for the sake of anybody who might